operating characteristics. So can you see my screen now?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So in the last class, we have gone through the different characteristics of DC generators. Okay, what are the characteristics? First one is the no load characteristics. This is a characteristics drawn between the generated voltage and the field current with the speed constant. So this characteristic is called as a saturation curve because after certain value of the field current, your terminal voltage is going to be constant, whatever may be the field current. So that's why that is called saturation has been reached. So the curve is also called as the saturation curve. Or why it is called the open circuit characteristics now? The armature circuit will be open circuited, so the load is not connected to the armature. That's why we are calling it as a open circuit characteristics. And it is magnetization. Why it is called magnetization? Because your field poles are magnetized with the help of the field current, and therefore you are getting the magnetization voltage. That's why this is called as a magnetization or no load magnetization curve. And the next characteristics what we have to discuss is the load characteristics, which is drawn between the terminal voltage versus the field current, keeping IA and speed both are constant. So load means there is some external load is connected. So as the load is varied, your IA will be varies. But we need to keep this IA constant. We'll see how to make it. And this is called as a load magnetization curve. And another characteristics which we have to discuss is the external characteristics. So this is drawn between the VT versus IL or IA. Both IF and speed are kept constant. And the armature characteristics. This is the last characteristics, and this is also called as a regulation curve. Regulation means it is a change in the no load voltage to the terminal voltage, full load terminal voltage. So the change in the voltage from no load to the full load and divided by VT. So this is called as a normally voltage regulation. This is a voltage regulation. It is in terms of percentage, and therefore it is must be multiplied with 100. So this will give you the difference, how the voltage will be changing from the no load condition to full load condition. Okay, so to have a perfect regulation, what must be some ampere turns, and we have to discuss that. So yesterday we have gone through the no load characteristics. Am I right? So the no load characteristics is drawn between the EG or EA versus. So here, this is a circuit diagram for conducting the no load test. So this is drawn with respect to EA, that is a no load voltage, or you can also call it as a EG. So EA versus IF with speed as a constant parameter. So as the speed is constant, and therefore we need to maintain the speed of your armature will be kept constant, and then you have to vary your generated voltage with respect to IF, and this is your IF which is represented here, and the current IL, or this is also equal to IA, and you can measure this as a terminal voltage or EG. So normally EG or EA you can calculate it. So this voltmeter indicating the EA which is developed under no load condition, because the switch S is, so this is called as a DPST switch, which is known as double pole. So here this is the pole 1 and pole 2. So double pole single through switch, double pole single through switch, which normally represented as DPST. So this DPST is always in open condition. Okay, and now we'll see the characteristic here. This is a no load characteristics which can be obtained, and this is known as the residual voltage because of some residual flux present in the field poles. And here this is a linear variation up to point D. So then there is a saturation. So for a small, if you increase the largest change in your IF, but very small change in your voltage you can observe here. Then we'll see the experimental setup, how to conduct in a electrical machines laboratory. So this was the circuit which we used for conducting the no load test. Okay. So here in a laboratory, we cannot go for any prime movers. That's why here the prime mover, which is known as a motor, which is used in electrical machines laboratories. Is it clear, everyone? So this is the experimental setup what we use in case of our electrical machines lab. Okay, so this is our generator. This is a generator for which we need to find the no load characteristics. No load characteristics must be obtained for this generator. So the generator converts the mechanical energy into your electrical energy. Am I right?
Yes, sir.
And therefore we need the mechanical energy, so we can go for any diesel engine or any other type of fuels for the mechanical energy obtaining. So instead of that, what we are using here is our DC motor. So the DC motor is coupled to the DC generator. Both the rotors are coupled together, and now this motor is run with the help of DC supply because it is converting the electrical energy into mechanical energy. And therefore the DC motor is connected across the 220 volts supply, and it is connected with a DPST switch, and a fuse is used to protect the motor from higher currents at the time of starting, and it is also used with the 3-point starter. So this starter limits the high starting currents. High starting current, we'll see why the starting current is very high in case of motors at the time of starting when we discuss about the motors. But for the analysis here, just you go through this. This is a shunt motor and it is having a shunt field winding here. This Z and ZZ is representing the shunt field winding. This is a shunt field winding. And this field winding is connected with a rheostat or variable resistance, which we call this is a rheostat, and it is a variable rheostat. Then if you adjust the positions of this rheostat, you can control the speed of your motor. Okay, the speed of a motor can be adjusted with the help of your prime mover. And now the field winding of your generator is represented here. This is a Z and ZZ. This is a shunt field winding of your shunt field, or not. That is actually our machine is a separately excited generators, and therefore we are separately exciting our field winding with the help of this DC source, and we are using a potential divider circuit which is used to obtain the variable voltage across the field winding of the generators. And here this ammeter in the potential divider circuit, which you can call it as a IF. This is a field winding which is measuring the field winding, and voltage across the field winding you can measure it as a VF. And now as you observe here, this is a generator armature terminals. A and AA are the generator armature terminals which are kept open. The load is not connected here. Just you observe, is there any load on this? There is no load. So we are connecting a voltmeter here just to measure the voltage across this armature terminals. So in previous case, we have discussed that here the circuit, the switch is open. Am I right or not? So here the switch is open. The switch is opened. So no load is connected. And therefore here directly I am going for the open circuiting of your generators, and we are measuring the voltage EG. So our no load characteristics can be obtained with respect to field current IF. Okay, so how you are getting this? This open circuit characteristics is nothing but it is having whatever may be the field winding, which is self-excited or separately excited. It is having certain voltage. This voltage is called as a residual voltage, and then this will be varies as a linear variation, and we need to represent here EG or EA, and on the x-axis this is your field current, and the variation of your field current with the variation of your EG with respect to your field current can be obtained like this. So this is linearly varies. Then after that, it will be having a constant value. Then if you have draw a dotted line, this is a linear variation, and this is a point D where your saturation starts. The saturation point is starting here. Okay. So this is called as a open circuit characteristics. So what is the procedure now? I will go in step by step. Okay. Initially, this circuit will be connected as per this circuit, and you see that the field rheostat, this field rheostat, and the motor must be in minimum condition, minimum resistance condition. This is a precaution which we have to take. Okay, and this field winding potential divider must be in the maximum position, or the field current must be zero. Initially this must be zero, IF must be zero, so your voltmeter reading is also zero across the field winding. But at this instant you may observe some 2 to 6 volts in a generated voltage. This is a 2 to 6 volts or 10 volts you can observe in the voltage which is connected across your generator, and this voltage is called as residual voltage. Residual voltage. So can you, when you observe this, once you start the motor, so here directly I'm telling that the 2 to 6 volts is obtained, but we have not started the motor yet. This voltage is also zero at the time of starting. Okay, so initially now the supply is given to the DPST switch, and now you close the DPST switch. The precautions you have to take it as the field rheostat must be minimum and the potential divider must be in the maximum position. Then after seeing this, then you close the DPST switch. Once the DPST switch is closed, now your supply, DC supply, will be given to your motor as well as to the field winding of your generator. Okay, and now next what we have to do is, so there is a handle here at the 3-point starter. With the help of this handle, we need to start the motor. We need to start the motor with the help of 3-point starter. Now the motor starts. The motor starts rotating. So when the motor rotating, then automatically this shaft is connected to the generator, and your generator is also rotating. Generator is also rotating with certain speed. Then next what we have to do is just using the tachometer to measure the speed, and you adjust the field winding of the motor, adjust the this potential rheostat of your DC motor, and then keep the speed at certain speed. So I am using a 1500 RPM. So keep the DC motor speed at 1500 RPM. And therefore your generator is also rotating at the 1500 RPM. Then can you observe any voltage here? Now you can observe only a small voltage, 2 to 6 volts, but your field current must be 0 and your terminal voltage across your field winding is also 0 because you are not changed any potential divider. So initially this field current is 0, the voltage across the field winding is 0. So you have to make a table. Okay, so take the observation table. So this observation table includes the field current and your generated voltage EG or EA. So initially, now the motor is running at the 1500 RPM. Then what voltage you can observe here? You can observe the field current as 0, and then let us take it as a 2 to 6 volts. So I can write here this as a 6 volts. Okay. Next what you have to do? So by using the handle here, you can change the position to this point. Just to change this position like this. Whenever you change this position, then a small current will be passing through this field winding. Small current will be passing here. Just you can observe that this current is 0.1. Now you can get a voltage of some 12 volts. Okay, and then next you change the position to next position. The current will be 0.2. Your voltage will be some 20. Okay, then similarly here also. Can you see what I'm doing here? Just I'm changing the potential divider positions so that your current will be changing. Then this will be now 40. And then you can move on to the maximum position. Then you can observe the field current as 0.4. Then it may be 70 or 80. The next another position. So this will be moved like this in steps. So you have to move on up to your rated voltage has been reached. So rated voltage is 220 volts. Okay, so in a no load condition, now you can also move. The no load characteristics can be obtained. So after reaching your 220 volts, you can move on up to 110 percentage to 125 percentage. That means 10 percentage extra or 25 percentage extra. So you can move on to up to 260 or 280 volts has been reached, so that your current will be some 1.2 or 1.3 like that. The field current may be exceeded by the rated values and your voltage may be increased up to 280 volts. Then once you reach the 280 volts mark, the maximum voltage, then bring back. Now bring back the potential divider positions to the initial position. Okay, initial position. Then the speed of a machine will be now make to 0. Not, it is not 0, so you minimize it, makes to the starting position. Okay, so initially now your position will be like this, then you bring back to your normal position, then open the DPST switch. Once the DPST switch has been opened, the electrical supply to the DC motor is disconnected, and therefore this motor is not rotating, and also your armature of your generator will be 0. So in this way, you can get the readings of the no load characteristics. Then you can draw the no load characteristics for a separately excited generator. Is it clear, everybody?
Yes, sir.
Yes?
Yes, sir.
Okay.
Yes, sir.
Now, next we will go through the load characteristics. So the load characteristics is drawn between which parameters? The load characteristics is drawn between the terminal voltage versus field current, keeping armature current and the speed constant. Am I right? Terminal voltage Vt versus If, keeping Ia and speed are constant. Okay. Now, so how can we obtain this load characteristics? Again, this is a circuit. I'm not going for the experimental circuit diagram now. Okay. So the load characteristics means we need to have certain amount of load, and therefore the switch is closed. The switch is closed. Initially, there are no load is present here. Okay, and I can assume that this is IA or IL. Am I right? Because IA is equal to IL, so I can calculate this as IA, and then this is your terminal voltage or EG. Okay, you can also call EA and terminal voltage. So how to get this? How to get this characteristics? So initially we need to run the generator at constant speed and close the switch. The first thing is we need to run the generator at a constant and rated speed. So the machine ratings are given. Okay, so run the generator at a constant and rated speed, then close the switch. So once the switch is closed, then the load is connected. The load is connected here. The next one, what we have to do is we need to keep IA also constant. Okay, the switch is closed, the rated current is adjusted. So we need to keep IA constant. So to keep the IA constant or rated value, whatever it may be. So if the machine rated current of this generator is 20 amps, let us assume, you can keep this 20 amps or also 10 amps or 15 amps like that. So as per your requirement, then you can keep IA constant. Let us assume that the current I am taking is 15 amps. So how can I adjust this? With the help of field current. With the help of field current, with varying IF, keep IA constant, and let us assume this is an example 15 amps. Okay, so 15 amps can be adjusted with the help of this load. So you have to apply certain amount of load which can carry a current of 15 amperes. Okay, the load is adjusted till it is taking a current of 15 amperes. Okay, the next, once it is fixed, IA is fixed, then you can get some terminal voltage. You'll get some terminal voltage or not, because it is having a load of RL and your value will be IA. So VT is equal to, VT is given as some IA into RL. This is your terminal voltage. So that can be directly obtained by this voltmeter. Then once this is fixed, next what we have to do is vary the load. Now after fixing this, next what we have to do? Vary the load. Vary the load. Then what are the consequences when you vary the load? Load vary చేసినప్పుడు ఏమవుతుంది చెప్పండి? When you vary the load, ఇప్పుడు మనం ఇంతకుముందు ఏం చేసాము? Just we adjusted the load to carry a current of 15 amps. Okay?
Sir, sorry for the disturbance, sir.
చెప్పండి.
Meeting only, sir. CR meeting.
Okay.
So left out, sir.
Okay.
Okay, sir. Thank you.
Next, anyone? So we have adjusted, just you can assume that this is a load. There are different loads are available. Okay. So each load is connected with certain switch. Just I will remove this. So this load will be connected with the switch. Okay. This is a load connection. Okay. Each one is carrying some 10 amps of load or 5 amps like that. So initially this switch was closed, this switch was closed, and this switch was closed. Okay. And then it is carrying a 15 amps of current. Then you change the volt, one open it, just you open it, what happens? The current will be changing, IA will changes, and terminal voltage is also changes. Am I right or not? If you
Yes, sir.
change the load, automatically IA will change, and therefore your terminal voltage is also changes. Okay, so keep this IA constant, then varying IF. Keep this IA constant by varying IF, and therefore you may have a change in the terminal voltage you can observe, and there is a change in your IF is also observed here. Am I right or not? Initially IF is giving certain amount of voltage VT for a current of IA is equal to 15 amps. Okay, then what I'm doing, I'm changing the load. Always the load is changed, therefore IA will be changes. To change the IA, we need to change IF. We need to change IF, and therefore you can have a different steps of IF, and according to that you may get a different voltages across the load terminal, at the across the loaded terminals or at the generated voltage. So you can also take EA. The generated voltage is also changes to the field current, because your field current IF, the relation between IF and EA is like this. Am I right? So as a field current is changes, your generated voltage changes. As the generated voltage changes, your terminal voltage is also changes. So you can observe a characteristics like this. You can observe a characteristics like this. So this is a load characteristics. Okay. So this characteristic consisting of two characteristics here. First one is a no load characteristics, which is drawn between EA and VT, and the next characteristics is the load characteristics. So as your IF changes, IF increases, your terminal voltage is increasing. Then what is the point here? What point you can observe here? This is a point when terminal voltage is zero, because your VT is zero. It indicates that the resistance, load resistance RL is equal to zero. When there is no load condition, when the no load condition is there, RL will be equal to 0, and therefore it is not carrying any current. IA will be 0, and therefore VT is also equal to 0. So this is the case you can observe here. Okay, so the difference between these two will give you the demagnetizing ampere turns, or the effect of the demagnetizing armature reaction you can observe. Armature demagnetizing effect of the armature reaction can be obtained from the characteristics of no load and load characteristics. Is it clear?
Yes, sir.
Yes?
Yes, sir.
Yes. Okay, so here the terminal voltage is zero, is nothing but it is a load resistance is zero. So that means the load is short circuited. You can call this as a load is short circuited here. There is no load resistance. Is it clear? Now, next we'll move on to the next characteristics, which is the external characteristics. And this is a circuit diagram for external characteristics. So the external characteristics can be obtained with the help of your terminal voltage versus IL or IA, the load current or armature current, because both are same, keeping field current and speed both are constant. Keeping field current and speed are constant or fixed values. So this is a connection diagram. So ఇక్కడ చూడండి నేను ఆర్మేచర్ డైరెక్ట్ గా చూపిస్తున్నాను. సో in extra laboratory if you go for that the circuit diagram this is connected in the previous case. Okay, ఇంతకుముందు నో లోడ్ లో సర్క్యూట్ డయాగ్రమ్ ఎక్స్పెరిమెంటల్ సెటప్ ఇచ్చాను కదా, the same circuit can be used, but the difference is your generator will be connected with a load. In that circuit only these two parts are present. Only these two parts are present. Am I right or not? And the no load condition, your armature is directly measured with a voltmeter, so the load is not connected there. Then if you connect the load and ammeter, this you can observe your current IL here. Okay, then how to get this? How to get this external characteristics? So now, initially, the generator is run with the rated speed with the help of prime mover. Generator is run at a rated speed with the help of prime mover. Once the generator is run at the rated speed, now you can adjust the field current IF. Okay, so this IF is adjusted. Just you increase the field current. So gradually this field current is increased. So here just the switch is kept open. The switch is kept open for some time. Now you increase the field current. So your generated voltage EA will be increased and it will reach as the rated value. You have to increase the field current. Okay, field current is increased to reach EA rated value. Okay, you assume that this rated value is 220 volts. So IF is increased. So as per our no load characteristics, if IF is increased, your generated voltage is increased. It reaches to the 220 volts. Okay, so the characteristics can be seen like this. So here IL and VT here I'll take. Then the load is not connected. So load current is zero only. The load current is zero only. Okay, so the load current is zero, but there is a certain amount of voltage, terminal voltage VT is equal to EA, because the generated voltage you can measure directly EA. So that is the terminal voltage. Because there is no load is connected, the terminal voltage is also equal to your generated voltage. As we know that generated voltage equation for any machine which we obtained as EG is equal to VT plus IA RA. Am I right? This is a generated voltage equation for separately excited machine. And we also seen the brush voltage drop, but it is very small. You can neglect this brush voltage drop. Okay, and that's why I'm not representing any brush voltage here. Then the generated voltage EG is equal to Vt plus Ia Ra, and as the machine is under no load condition, okay, at no load, the switch is not closed yet, and therefore Ia will be equal to 0. It is not carrying any current, and therefore your terminal voltage Vt is equal to Ea. The terminal voltage Vt is equal to Ea, so that can be obtained here. Vt is equal to Ea under no load condition because IL will be equal to 0. Okay, so once now your generator is reaching the rated value, next step is close the switch. Close the switch, and therefore load is connected. Load is connected. So as the load is connected now, this is closed like this, and this is connected. The load is connected. Next, as the load is connected, now vary the load in steps. Vary the load in steps. So whenever there is a variation in the load, there will be some variation in your armature current or load current. Okay, and therefore your terminal voltage can be obtained as Vt is equal to Eg minus IaRa. Can I write like this? The new voltage will be like this now. Vt is equal to Eg minus IaRa. And because of this, now as the load is applied, so you can observe some current here. You can see some current Ia, and because of this Ia, there is a voltage drop takes place across the armature winding, and therefore the net terminal voltage will be gets reduced. For lower loads, for small values of armature current, the change in the terminal voltage from no load value Eg or Ea is very, very small, and therefore you can observe that it is a constant up to certain point. So this is a constant load. This dotted line is a no load value, and here for smaller values of load currents, Vt is almost equal to the terminal no load voltage. Then after that, if you go on increasing the load current, this will be decreases like this. There is a decrease in voltage from the no load value because here IaRa drop will be there, and this drop will be reducing your terminal voltage. So this is your characteristics like this. This like this your voltage will be gets reduced. Okay, then you can see the characteristics here. These are the characteristics which you can observe from the no load value. Okay, so here this is a EA. Point A is nothing but the no load voltage. This is the dotted line is the constant value of no load voltage. Then there will be a small drop in the voltage like this. Okay, and again there is a second curve is there, one curve 1 and curve 2. Here the curve 1 indicates the external characteristics, which is drawn between your normally terminal voltage versus IL, and the second one is the internal characteristics, which is normally drawn between your terminal voltage, okay, by adding armature reaction effect or terminal voltage versus Ia, okay, or Eg versus Ia. So here there is a small drop here, this drop in this voltage, and the drop here, this drop, this is a drop in the voltage. This drop is due to the armature reaction. We have seen what is the effect of armature reaction. This armature reaction is having the two effects. One is a demagnetization effect and a cross magnetization effect. Am I right? So because of this demagnetization, the net flux will be gets reduced. Whenever the net flux is reduced, your generated voltage gets reduced. When we see these effects, when the generator is loaded under no load condition, there is no armature reaction effect, because armature current is very small under no load conditions, and therefore there is no effect of the armature reaction on the main flux and also on the generated voltage. So whenever the generator is loaded, then only your armature current is comes into picture, and therefore it will produce the armature flux, and this armature flux will produce some effect on the main flux. This effect is called as an armature reaction. Because of this armature reaction, there will be some reduction in the net voltage. And that's why that net voltage is considered here. This is known as the internal characteristics. Okay, so if you subtract your armature reaction voltage from the no load voltage, then you will get a internal characteristics. And then if you subtract IA RA drop, this is nothing but your armature resistance drop, IA RA drop, then you will get the external characteristics. So again, there is a decrease in the voltage. This is the external characteristics. The characteristics one is known as the external characteristics. Is it clear? And also,
Yes,
so
sir.
here also you can get the regulation from this. The regulation, percentage regulation is nothing but the terminal voltage EA minus VT by VT into 100. So this is your regulation voltage that can be obtained for the separately excited generators. Okay. So I will stop here. So tomorrow we will discuss about the armature characteristics or regulation curve for the separately excited machines or generators. And again, we'll see the same characteristics for shunt generator also. Okay, so tomorrow we'll completely discuss about the shunt generators characteristics. Okay, shunt, if possible, we will finish a series and compound generators also, because all the characteristics are similar to the characteristics what we discussed here. Okay. So now I will stop here. Do you have any doubts? Just if you have any doubts, you can share it in the chat box so that I can answer you. Okay.